Hello physics students. Today we begin our studies of the electromagnetic force. Before we do that, I just want to remind you that we talked about the four forces of nature in an earlier video, and I just want to call your attention to the fact that of the four forces, we have the strong force. That's within the nucleus of an atom. It's the strongest force in all of nature, in all of the universe. But again, never felt because it's inside the nucleus, holding the nucleus of an atom together. Strong force. Then we have the electromagnetic force, the weak force, and the force of gravity, the four forces in nature. Last year in mechanics, we studied the force of gravity, that any two masses attract each other always. There's no repulsion. Gravity always attracts. It can be between your pencil and your notebook. They attract any two masses. Okay, so we studied that already. And then so this entire year will be focused on understanding the second force, the electromagnetic force. There's electricity, there's magnetism, they're part of the same force. Okay? So by now, you should have printed out our unit plan, the electrostatics of point charges. So what we're going to do, we're going to begin our understanding of electricity and magnetism, a very complex topic, with just the simple situation of point charges like protons and electrons that are fixed in space, meaning their velocity remains zero and the acceleration remains zero. So they're just glued in place and they're not moving or accelerating. And within this topic, what we're going to do is lay the groundwork of four ideas within electrostatics, charges that are not moving. And the four ideas that we're going to be using for a good half of this course repeatedly, which we need a foundation in this topic, is force, electric field, electric potential energy, and electric potential or voltage. So those four ideas, force, electric field, energy, and potential or voltage, we're going to study in this topic, but you really have to get them down in your mind, firmly rooted, because those four ideas will be recycled again and again. If you don't get a full, solid grasp of them in this topic, you're going to struggle for half the course. Okay? All right, so let's begin. What I have here, some notes already written out for you. So I'll pause the video to allow you a chance to catch up and write these down in your notebook. Okay, so electrostatic force, the symbol for it is F subscript E. Like in gravity, we had a G over here. Fg meant force of gravity. Fe is force electrostatic. So we have two charges, maybe a proton and an electron, or two pieces of dust that are charged up. We'll talk more about how charge is acquired for objects other than protons and electrons in a later topic, a later video. So now, when it came to gravity, what caused the force was mass, kilograms. Okay? So in this instance, it's not kilograms, it's charge, so we need a new symbol instead of M. And we use the symbol for Q for charge. So we have Q1 and Q2, the two charges of each of those. And they're measured in coulombs, which you abbreviate with a C, a capital C. And they're a certain distance apart. The variable r is used because, like gravity, very often with charges we have orbits occurring, like when an electron orbits a proton in a hydrogen atom, which traces out a sphere or circle or a sphere. So that's like the radius of orbit, so that's why the symbol r is used instead of something like maybe d. In this case, I'm having the forces, the objects repel each other. As I said, gravity always attracts, but with charges, you can have attraction or repulsion. If the two charges are positive or they're both negative, then you'll have repulsion. So this might be like a proton and a proton, then they repel, or an electron and an electron, and then they repel. But if the two charges are opposite, plus minus or minus plus, then we would have the arrows switching inward. The other thing I want to point out is that these arrows are the same length. Newton's third law is still holds here. So this could be like 1,000,000 coulombs, and this could be like 0.0001 coulombs. It doesn't matter that one is bigger than the other. The forces are always the same on either object. So Newton's third law in mechanics, in gravity, in electricity and magnetism still applies. All right, so here's the big equation. F is kqqq over r squared with the subscripts of the two charges. So it looks like the gravity formula, except instead of the capital G, we need a new constant for the electrostatic force. And we use Coulomb's constant K, 8.99 times 10 to the 9th Newton meters squared over coulombs squared. And you can round this to 9.0, and it's perfectly fine. You don't lose any credit if you just say 9 times 10 to the 9th. I also want to point out that there's actually a more fundamental constant called epsilon 0. This is a Greek letter. It's like a backwards 3. Epsilon with a subscript 0. It comes up more in later topics. This is used more than K. And epsilon 0 is given by this, 8.85 10 to minus 12, and there are the units. If you do 1 divided by parentheses 4 pi and that number, you would get about 9 times 10 to the 9th. So they're equivalent. In this unit, we're pretty much going to focus with the K constant because, like I said, I just want to mention this so it's familiar for later in the next topic. Okay, so, and then I have the rest of the information here. So that's it. Opposite charges attract, the same charges repel each other. And with this many newtons. What I'm going to do is now just do an example problem to, kind of familiarize you with the problem solving related to this equation. Okay. Oh, here we go. Okay. So I have 3 charges laid out on an axis like this. Okay. This charge is at x equals 0. This is at x equals 0.2 meters. So they're just laid out on the x-axis. In part A of this question asks okay, by the way, I just want to mention that this symbol is like the coefficient of friction mu. It is also used as a metric prefix. So for example, I could have 1 millimeter or 1 kilometer. And milli, we know, means 10 to the minus third. And kilometer means 10 to the minus third, right? So we're familiar with those. Well, there are other prefixes for things beyond 1,000 or divided by 1,000. Micro is times 10 to the minus sixth of anything. So you could have a micrometer, and that would be a millionth of a meter. Or a microcoulomb is a millionth of a coulomb. Okay? So these are just little tiny bits of charge on this x-axis, maybe pieces of dust that are charged up. And so the question is, what is the F net in this current location, and where can I put this charge for it to have a net force of 0 caused by the other two charges? I'll pause the video here to give you a chance to jot this example problem down. Okay, so let's begin with part A. So, what I first have to think about is how these two charges are affecting this middle charge. This 5 microcoulomb charge is positive, and this is positive, so these two repel each other. So that this positive is going to push that positive away from it to the right. So I'll put F5 because that's the force from the 5 microcoulomb. And I put it down below because otherwise the markers get all messed up when you start tracing over. But really it's along the axis. And then this charge over here, here we go, dropped it. It's negative and this is positive. Opposites attract. So this is attracting this one, and attracting it means it's pulling it to the right as well. So it pulls it with some lesser number of newtons. I'm going to call it F1 because this is a 1 microcoulomb charge. So these two forces are in the same direction. I need to find them so that I could find the net force or calculate the net force. So the first thing that I could do is find F5 by using Coulombs Law. Let's see if I could squeeze it in here. I used 9 times 10 to the 9th instead of 8.99. Q1 is 5 times 10 to the minus 6 coulombs. And the other one is 2 times 10 to the minus 6 coulombs. And they are how far apart? Well, from here to here. And if this is 0.2 meters, these two are 0.1 apart. So I put this . Okay, so this comes out to be 9.0 newtons. So that's how long that arrow is. I need to find the other arrow, so I'm going to find the force between these two. Once again, I use Coulombs Law, which is what that is, this equation. I should have mentioned it's Coulombs Law is what it's called. And I put in my numbers, 9 times 10 to the 9th. And then I've got 2 microcoulombs, which is 2 times 10 to the minus 6 coulombs, and 1 microcoulomb. And when I plug that in, I get 1.8 newtons. Now, some of you might be saying, I thought this is a negative charge. Why did I plug in the negative? I'll explain that in a minute. What I'm going to do is just pause the video to allow you to copy this down for a second. Okay, why did I leave the minus off? I would recommend whenever you use this equation, you never plug in negatives. Because if I plugged in a minus here, I would end up with a negative there. And then when I'm trying to find the net force and I add these two together, I'd actually be subtracting them as if the forces were in opposite directions. So the minus signs, I recommend again never to put them into the equations. They're more to figure out whether this arrow points to the right. Because they're both positive, it points to the right. This negative tells me that since this is positive, this force also points to the right, attracting here. Once I drew this arrow in the right direction instead of the left, I've already completely used the information of the negative charge here. So I've already included the negative with the direction of this arrow. And now, when I say F net, I say, okay, I got a rightward 9 newtons, and I've got a rightward 1.8 newtons. So because they're both to the right, I'm going to add those to get the net force. So F net will equal 9.0 newtons plus 1.8 newtons, or 10.8 newtons. Now, maybe before we jot this down, I could remind you of some fancy notation that we use. If we wanted to say it's in the positive x-axis direction, we could do that this way. We could say that this is plus 10.8 newtons I hat. Okay? And I hat means in the x direction. If I put negative 10.8 I hat, that means it'll go to the left. All right, let me pause the video and give you a chance to jot this down. Okay, recall that there's a part B to this question. Where can we put this charge for the net force to be 0? So I'm going to erase this for part B. Okay. And let me just quickly resketch. Okay, I had the 5 over here. Five microcoulombs. And the negative 1 microcoulombs here. And recall this was x equals 0. Now, we just figured out that if I put this charge in the middle, since it's positive, as I said, this will repel the positive, and so this goes this way, F5, and this negative attracts that positive, which means it also goes to the right. And so there's no way that I can put this somewhere in the middle and create a net force of 0. Because no matter what these are, they're both in the same direction. They have to be going opposite directions for them to add to 0. So maybe here, maybe here. Let's try over here. So I put the positive charge here, the positive 2 microcoulombs. If I put it here, it'll be attracted to this 5. Repelled. Positive, positive, repels away. So this 5, which I drew in blue, will go this way. Now, this positive and this negative will attract each other. But I'm going to draw this arrow shorter because it's always shorter in this region to the left. Why? This 5 is a bigger charge and it's closer. So in Coulombs Law, we would have both a bigger numerator because of the Q being larger and a smaller denominator than this radius right here. So this arrow will always be longer. It might be like 20 and this will be like 2 or something like that. So they, even though they're opposite directions, good sign, the magnitudes will never be equal. They have to be equal and opposite. The only place for this to possibly have a net force of 0 is if we put the plus 2 microcoulombs in this region to the right of both charges. Over here, what will happen is this positive and this positive will repel each other. And this negative and this positive will attract each other. Oops, wrong color. And only here is it possible for these forces to be equal. Because when it comes to this 5 microcoulomb charge being bigger than the 1 microcoulomb, so this is bigger for this charge, but we also have a bigger radius. So bigger charge further away offsets those two effects, so it's possible for these two forces to be balanced here. So that's the reasoning. All that thinking has to be done before you even start calculating. Thinking about which of these three regions, to the left of the charges, between the two charges, or to the right of both charges, is it possible for the force to balance between coming from these two charges on the third? So remember that this was x equals 0. So we also need the radii. Actually, maybe what I'll do before I do that, I'm going to leave some space here. And I'm going to say this, all that thinking in the following manner. I'm going to say F1 will equal F5. You know what? Maybe I'll stick with color coordination. Oops. Okay, so they're both equal and opposite, and that ensures that the net force is 0. So I have K. I'm going to not plug in the number because it's on both sides. It'll cancel out. You'll see what I mean in a second. And 2 microcoulombs. Now, what radius do I plug in for these two charges? So I got to now think about radii, and this is how I could do it. So this is obviously x, the radius between these two charges. Between these two charges, what's this radius? Well, if you think about it, this is x, and this is 0.2. So that means that this is x minus 0.2 meters. X 0.2. So this is x minus 0.2 is that distance. So that's what goes into the denominator, the radius between these two forces, which is F1. So 0.2 minus, or x minus 0.2. Yeah, I guess I could leave the units. Okay. That's going to equal Okay. Okay. Q1, Q2, this and this, right? So 5 and 2 microcoulombs, that's what goes into the charges here. 5 times 10 to the minus 6 coulombs. And 2 times 10 to the minus 6 coulombs. All over x squared. Okay, so I'll pause the video for a second, allow you to copy this down. Okay, so what I can do is divide both sides by k. I can divide away all the coulombs units. I could divide away the 10 to the minus 6th with this 10 to the minus 6th. This 10 to the minus 6th with this 10 to the minus 6th. And so all that survives on this side is 2 times 1 over this, which is 2 over and on this side, 5 times 2, which is 10. Oh, you know what? Maybe I should have divided the 2 out also. Well, I guess. And so I could say even 1 and 5. Okay. What I'm going to do is cross multiply x squared times, okay, x squared times 1, 5 times this parenthesis term, what I'm going to do now is take the square root of both sides. So leaving me x on this side, and on this side, radical 5, x minus 0.2. And at this point, I'm just solving for x. So I can distribute the radical 5. And then maybe what I'll do is subtract this to this side and add this to this side. So I have positive 0.2 radical 5 equals radical 5x minus 1x. And I can factor out the x, which would give me and lastly, I could divide by that parenthesis term on the right side and get and that's the location where this 2 can be placed to create a net force of 0 caused by these 2 other charges. All right, I'll pause the video to give you a chance to jot this down. Okay, so that's it. That's our first exposure here to the electromagnetic force. Again, remember, we're just dealing in this topic with charges that are fixed in place with 0 velocity and 0 acceleration. So they're just stationary. And today we learned that 2 charges stationary either attract each other or repel each other. We figured out how to calculate using what we call Coulombs Law, that equation K, F equals K, Q1, Q2 divided by R squared. And then we learned a little bit about how these forces are vectors and how to account and find for net force in the middle. or over here, for instance. And we also learned how to find the location where you could place that third charge so that the net force is 0. Okay, so that's it for today, and I'll see you in the next video.